Got it. Got it. Okay. I'm Kevin Appert. I'm the program chair. Welcome to the May Silicon Valley Fourth Interest Zoom meeting. And we were talking a little bit before the recorder started about the olden days at Stanford, and I interrupted Brad because he wanted to say something. So what did you want to say, Brad?
I was going to say, I think one of the other problems that we struggled with at Stanford was the problem of when the audience would ask questions, unless we were very careful about walking a microphone around the room, we would oftentimes hear the answer from the speaker, but not the question. And so I think that was another sort of negative.
Or you'd hear or some other ne'er-do-wells yelling, "Repeat the question." I've had the experience talking in I've had the experience at other presentations where the questioners are supposed to speak into the mic for the posterity, whatever YouTube video, whatever recording was being made, and I would yell, "Speak into the mic!" And the guy said, "I don't need the mic." And it's like, okay, but that's just me. I think going forward, when and if we can get back to Stanford, I would like to continue this as a Zoom meeting and specify to presenters that they will need to present to a Zoom meeting, and there'll be people in the room that will be watching them live, and the Zoom meeting will be up on the big screen, but it will just be a viewing party and with some local presenters, but the presenters will be Zoom presenters. And it may be that we'll have afternoon sessions that will be on camera, that will be, one of a kind things that won't turn into YouTube videos and things.
We've been doing some Ham Radio Club meetings that are Zoom, dual Zoom, and it works fairly well. The one major hiccup is if anybody in the room takes their cell phone and tunes into the Zoom meeting, you start to get echoes, and you can't find out who in the room is generating the echoes, and that takes the meeting down with the echoes. But anyway, with a little bit of care, you can switch between speaker and screen view, and so it's worked quite well with the Ham meetings.
Yeah, I've had the experience where I'm talking on the phone and my Bluetooth suddenly stops working, either because I'm passing some transmitter or something. Anyway, Bluetooth sometimes just drops out, stops working, and the phone is working as a phone. Unfortunately, it's sitting on my on the seat of the car, or on my belt, or some other place where the guy on the other end can't hear me, or I can't hear them. It's very frustrating when that happens in the middle of a conversation. So on with the show. Again, May Silicon Valley Fourth Interest Group. We'll be talking, I guess, more about what we'll do in the future. When Dave tells us that we're welcome back at Stanford. I don't want to crowd their decisions about that, or lack of decisions. I guess it's easier to ask for forgiveness than permission. What's the prospects there, Dave? What sort of timeline are they on as of us getting back into the Stanford venue?
Well, there's a couple more weeks till graduation, and then there's a summer session, which I think will be. I'm not sure how much stuff would be going on in the building, and the situation is that we can use room 200 if nobody else is using it.
Will there be utilities, air conditioning?
Oh, sure, yeah. So I can do my best to figure out, to ask what is scheduled on our normal fourth meeting days, and you guys can make a decision whether or not to take advantage of the room or not.
Should we look, maybe thinking about July as a target?
I can do that. Well, so first let me find out if anything is going on for the July meeting. If something is going on, the people that have reserved that room, will get that room. But there are other smaller rooms in that building that we can use as well. We don't need to have room 200. We can use one of the smaller rooms.
Yeah.
That's okay.
Are those reservable by others?
Yeah, they are, but our group, because it isn't really a Stanford group, doesn't have the ability to reserve those rooms.
Okay. So we've had a bit of blather. I think that's enough. Let's get on with the program. Klaus?
Yes.
Introduce yourself and get on with the show.
Yeah, there is not much to introduce, but I will screen share first. Let's see how this works. Yes, this is what I intended. Yeah, I'm programming for since 1980, and since 2001 I have been designing microCore as a force processor that fits into FPGAs, and this is part 2 of its VHDL code and its structure. As a reminder, how do I get to the next screen? As a reminder, this is the structure of the VHDL code. And today I will primarily talk about microcontrol, which is basically the internal engine that does the instruction decoding and defines all internal registers. And if we have enough time left, I will talk briefly about the cold bootloader, which is also an interesting piece. So let's get into microcontrol.vhd. This is it. It has, of course, an entity interface that is not very important here. We define various signals, and the interesting ones are actually, what is interesting to note, also the instruction decoder, the microcontrol, gets its primary signal from the microbus, namely the clock. The clock enable, what I call sources. These are all the internal registers that have been defined in microCore and the flag register. And here we already see all the internal registers and internal signals of microCore, which is top of stack, next of stack, top of return stack, the status register, the data stack pointer, the return stack pointer, the program counter, an instruction register that has a very special role, which I will explain later, plus the chain bit. And then we have a data register, which is intermediate storage for plus store if it happens in external memory. And so this defines a record of registers, and here these registers are actually instantiated. So the actual registers used in microcore I call R as in registers. And then I have a second image of all these register names, which are called Rn. Now that is a technique that has been used for the first time, I believe, by a Swedish guy who did quite a number of designs for the European Space Agency. And it's rather tricky because it cuts the computation of new content for the registers from actually updating the registers. And first I will talk, let me look into my notes at the signals, which we are currently doing, and then the microcore registers, and now we go to the actual instruction decoding, which starts on line 357. Here we are. This is the instruction decoder proper, and it is a very large, from here to the end of the file, just to show you how much it is. It goes on and on and on and on. And it starts at 357. So it's an asynchronous process, and I have to make a list of all signal names that change the state of the internal asynchronous process. In Vhdl 2008, I could just say all. But if for legacy reasons and a design environment only supports Vhdl 93, I have written this in 93, which is true for all of microCore. So you can also use it on legacy designs that don't support anything above Vhdl 93 in its synthesizer. So we have a number of variables that are only valid inside of this process. Not very important for the single items. And then there are registers for floating point support. There are again alias definitions, which just I can refer with a name to, I mean, the instruction bit 7, or the instruction, the literal inside a literal instruction, which is everything but bit 7. So I have handy names for that. And then come a number of procedure definitions. I leave out that. Push the stack. I go into this in detail. So we set the right memory bit of the data stack memory to 1. And what do we do here? We copy, but here you see the function of Rn. Rn will be the state, Rn.nos will be the state of next of stack in the next cycle. And I assign the TOS register to Rnos. Oh yeah, that's clear. It's a push, so the TOS goes into NOS. NOS goes into the data stack memory. So this is the right data of the data stack memory. We use the DS push address. We come to that later, how this is defined, to the data stack address register. And then we also update the data stack pointer, which becomes also ds push. So this is a procedure push stack. And later on, I can just say push stack semicolon to do all of this. The same, no, then I define pop stack, which is the other way around. Push return stack, pop return stack, call a trap address, a procedure for doing a branch, and these are all the procedures. And then the begin marks the point where the actual code begins. And here you see what I defined as DSP push, DSP push. This is tricky code. I mean, if I have a single task system, everything is simple. I add one to the DSP, but if we have multiple tasks, we also have multiple stacks. And so the data stack pointer not only contains the relative, it not only contains the address of the stack item, but it also contains bits for the stack that I'm talking about, that the current task is using. So this is a little bit more complicated. And I have set up the code in such a way that if the stack overflows, it never goes into a different stack area for a different task, but it just wraps around within itself. Then there is the function toss power of 2. This is an interesting one. This will create static code in Vhdl, and what it does, it converts a number like 7 into its power of 2, which is 128. Now, why would I want why would I need this? This code allows me to do a barrel shifter with just multiplying the number that I want to shift with a proper number and toss power of 2. So if I want to do 7 shifts to the left or the right, I multiply my number in toss by 128, and that is effectively then a barrel shift by 7 positions. Then starts a section of code that initializes the microcore registers. Now, again, remember, we have, and here it becomes very clear, we have the R register, which is a collection of all internal registers which are currently set. And Rn will become the internal registers in the next cycle. So to start the whole game, I first set Rn equivalent or identical to the current state of the registers. And in the following code, I can modify individual registers in Rn without affecting, for the time being, anything else. We initialize the data stack memory, so we set it to read. The data stack address is the stack pointer, and the data that I write to the data stack memory is always RNOS. We initialize arithmetic. How do I set this? I initialize the arithmetic to do an indirect, to compute a relative branch address. So I take the content of toss, which is the offset, and and the PC as the second input to the adder, and the result then is the branch address, the target of a relative branch. I initialized multiplicand and multiplier for the multiplier, floating point initialization, registers, return stack. Now these are important address comparisons. The data memory falls into three parts. So there are the registers which reside at the top of the data space. And so if I address a register, this function becomes true. If it is a data cache, which means the data memory is inside of the FPGA, then this is true as long as the data address, the TOS is equals 0. That means everything that is, all the bits that are above the cache address have to be set to 0 in order to be an internal address. And then the external RAM is just the opposite. It is if everything that is above the beginning of the external memory. So memory enable, external enable, memory write are all initialized to 0. And then the program memory address is initialized, as well as is the program counter. The program counter is always set to the actual address of the program memory in this instruction, incremented by 1. And so I also have can read and write program memory as data, and so I need two signals for that, program memory write and read, and they are also set to 0. The end result of this initialization is that if I don't do anything else, the processor will execute a no-op, which we can see here when we go into the case instruction construct. So when I execute the no-op instruction, I don't do anything else but what has been done in initialization here. I will skip the interrupt here, but I will talk about the literal instructions. So if the literal bit is set in the instruction, this is the most significant bit, and all the literal instruction have it set, and all the operators, the opcodes, have the most significant bit set to 0. So the first thing I do is, in the next cycle, I will set the lit bit in the status register, and if at present, when I execute this instruction, the slit bit is not set, then this is the first literal instruction in the instruction stream. So I push the stack and I sign extend the 7-bit, the 7 bits of the literal instruction. I sign extend this and store it into NOS, into RIN of TOS for the next cycle. If the status, the lit bit in the status register is already set, then I come into the else clause and I just push what is in TOS right now by 7 bits. So I start, I take add TOS von data width -8 down to 0 and append the 7 bits of the literal instruction to it on the right side. And this way I can accumulate large magnitude numbers by a series of literal instructions. So if the lit bit is set to 0, I come to the opcodes, and we go into a very large case statement. So from here to the very end of the file, this is the large case statement. But as you can see, I mean, instructions are quite simple. So the drop instruction is just a pop stack, which was a procedure I talked about earlier. A dupe is a push stack. A query dupe is, well, if TOS is unequal to 0, I push the stack. And if it is 0, I don't do anything. The swap is, as you can see, put the current TOS into NOS in the next cycle and put the current NOS into TOS in the next cycle, and over and over. So these are all the stack operators, and I have been generous by including also ROT and minus ROT, which is possible because I have available TOS, NOS, and the top item of the data stack memory. And so these become one cycle instructions. Nip, tuck, and under. Then we have return stack instructions, rpush, rpop. So rpush is the rfrom, and rpop is the, oh no, rpush is pop the stack. Rpush is pushing on the return stack. So we pop the stack, we push the return stack, and then we put rtos into TOR. And so on. I also have a single instruction I for do loops, which are possible because I can access not only the top of return stack, because this is the return stack register, but I can also access the second item on the return stack, because this is the top item of the data memory where the return stack is located. Then we have various data memory accesses, which become more or less complicated because there are these 3 regions that I talked about. We have registers, we have the external RAM, and we have the internal RAM. And in all cases, I do have different enabled signals, which can be used in the remaining part of the microcore design. Here is something that I want to briefly mention. Given the structure of the internal data memories, reading a data memory is a 2-cycle instruction for microcore. Because in the first cycle, I have to set the address, and then in the second cycle, I can fetch the content of the memory location. And I do this by setting, as part of the load instruction, if it is in internal memory, then I chain an instruction, so to speak, to the load instruction, which is I have called memory to NOS. And here is actually memory to NOS, and it saves the read data of the memory into the NOS register in the next cycle. So OpStore also has registers, external RAM, data cache. Then for the heck of it, if you select the extended instruction set, I have a fetch instruction itself. Yeah, this I have to add. If you say upload, then the address remains on the stack in the top of stack register, and the content goes into NOS. And this is nice because you can do a chain of fetches or stores by just doing simple address arithmetic on the address on top, and then so this way you can access records quite efficiently. So there's also a fetch because it can be done in one instruction. It doesn't do a push, it just replaces the address by its content. And the store instruction, you always have to get rid of 2 items on the data stack, which is not possible in microcore in one cycle. So if you have a for store, then you always do a store instruction followed by a drop in order to give you the for store. Then there is a mechanism that you can address into the return stack, because remember, the return stack is in data memory, so I can also access it using a fetch or store for the data memory, but I need to know the address where the return stack is. And oplocal is a function in TOS. There is an index into the return stack, so I can retrieve the memory address of the second item of the return stack by saying one oplocal, and then I can use the actual address of the data memory to do sensible things with the return stack, like accessing local variables or local vectors. Also, I have in the extended instruction set, I have a plus store instruction, which is a 2-cycle instruction, which does an indivisible plus store. So you can use plus store for synchronizing interrupts and tasks. Internal registers, well, there's only the status register, where you can set efficiently single bits in the status register. Then there are program memory instructions to access the program memory as data. And then we have the branches, the call, the exit, the interrupt return. Yeah, let me add this. The interrupt, if the interrupt is executed, I do not just a call to the interrupt vector, but I push the status register on the return stack in the same cycle. So I have a special interrupt return, which not only does an exit, but it also restores the status register from the top of stack. And that makes for very, very efficient interrupt processing. There is the opcode for the pause instruction, which does a call to the pause trap. Then we have a break instruction. Well, a does instruction. I don't want to get into this any further. Then we have the unary arithmetic, not 0 equals, 0 less, shift right with carry. These are shift left with carry. And I want to talk a little bit more about this instruction, which I called mshift. This is something that I added to microCore 3 years ago or so, because for a very long time it was quite unclear what kind of shift instructions are really needed and necessary. And then finally I came up with the mshift instruction, which is actually a barrel shifter, and it is the core of all the shift operations if a multiplier is present in the FPGA. Because the input to mshift is a single data item and the output is 2 data items in TOS and NOS, which is the shifted result of the number in TOS. So if I shift 3 places to the right, then there remains these 3 bits in TOS, and the remainder that has not been shifted remains in NOS. And this way, for instance, 2 times becomes 1 mshift drop, because I throw away what I don't need. And also a cryptographically very important instruction is the rotate instruction, which shifts a data item by most of the time 8 places, and then appends the bits that have been shifted out at the right side of the number. So that is rotate, and that can be done with mshift very easily. It is number of shifts, mshift OR, and that gives you the rotate. There's also provision for mshift if there is no multiplier, and that, you see, it just complicates the code. There is also an MA shift, which is an arithmetic shift that replicates the sign bit instead of shifting zeros in from the left. Then there is binary arithmetic. We all know that, add, ADC, and so on. Also, an interesting one is the saturated arithmetic, which is important for control loops, because if it produces an overflow, then it returns either the maximum or the minimum number that can be represented, and that leads to the behavior that control loops become stable. I mean, they may run out of steam, so to speak, in that they cannot actually progress as fast as necessary, but at least the control loops don't show erratic behavior, which would happen if you use a non-saturated add with an overflow in a control loop. Then we have these p-add, p-ADC are 2-dup plus and 2-dup plus carry and so on. And then comes complex arithmetic, which is depending on whether we have a hardware multiplier. If you have a hardware multiplier, this is very simple. I put NOS into the multiplicand and TOS into the multiplier, and then I save the product, which is computed asynchronously within this one cycle into TOS and NOS. If there is no multiplier, we have a single step multiply instruction. We have a last multiply, we have a signed multiply, and that is only valid if we have a multiplier on board. We have a divide single step, then we have starting and ending division. Excuse me, I'm talking about division. We have the division step proper, which is this guy. We have a starting unsigned division step. We have a last unsigned division step. And then we have a starting signed division step, and we have a starting, we have a last signed division step. And here you see this already becomes quite complicated, and especially the computation of the overflow bit is not simple. So you see this here is the logical equation for the overflow in the signed case, and then if this is true, we assign a 1 to the overflow bit. Now, an interesting question is, how do I test the multiply and the divide that they were correctly? This becomes very simple in microCore because I can set the data widths. And if I want to do a full test of all possible cases in multiply and design, I just reduce microCore to a 16-bit version. And in the 16-bit version, I can do a full test within, I think it's 3 hours or so. And then I just trust that I use higher data width than 16 bits. This will all be still valid. And I think this is a valid assumption because already in the 16-bit case, I have tested all the fringe cases. Then there is also a square root single step instruction, which handles 2 bits in every step. There are special instructions for the flags. An interesting one is less. This is the core of the less and greater instructions, which are not so trivial to code as Bill might remember. And then come a number of multiply floating point instruction, which is the f multiply, which is the star dot instruction in force. We have a logarithm step instruction, which is possible if we have a 1-cycle multiplier on board. There is a normalize primitive that is an auto repeat instruction, which keeps repeating until the first position of the mantissa is set to the opposite bit as a sign. And what is nice about it can be interrupted in between any single shift until the normalize has finished. There is an instruction which you can see is also quite complicated, which converts 2 numbers which are the mantissa in NOS and the exponent in TOS into a packed floating point number. And then we also have the opposite. It takes a packed floating point number and makes a mantissa and an exponent out of it. And if we have any other instruction, it is either a no-op, or if the instruction falls into the user space of the instructions, then we handle it as a trap instruction. And this is a large case statement. And if you want to add application-specific instructions, all you have to do to the microcontrol.vhdl file is add another when clause to this large case statement, and that's it. So the next thing, after talking about the decoder, I want to go to line 216. And this is the sequential part. So the big decoding, asynchronous decoding, is the asynchronous part of decoding an instruction. And this is the synchronous part, because with every rising edge of the clock, and if the clock enable is set, we basically do different things depending on whether the pause signal is raised, whether, well, let's not talk about this. This has to do with the umbilical interface to the host, or we have a normal force instruction. And here you see the assignment. The Rn that we computed in the last case statement is assigned to the R register set and becomes the new state of the internal registers. But if we have a pause, then we set back the program counter to the current program address, because we have to re-execute the instruction that could not be processed. We push the pause operator into an instruction register, and we set a 1-bit signal to 1 that says this is now there is now an instruction in the instruction register that has to be executed instead of the output of the program memory, and namely this is the operator for the pause instruction. And then the pause instruction does a push of the program counter and goes to the pause trap. If there is just an exit in the pause trap, then because of this line here, I do an exit that retrieves the return address from the return stack, and in essence I re-execute the paused instruction, and that process will repeat until this condition is no longer met. That means the data that I want to access is available. Yes, I talked about this instruction register. This is on line 361. Here you see the instruction. The instruction that I currently execute comes from two sources. It's either the read data of the program memory, if the chain signal is 0, or it is the content of the instruction register. So much about microcontrol. And now I want to take a look at the 2-cycle instructions, which are, the 2-cycle instructions which are present in core. So what I have talked about previously is the microcore. The next instruction that gets interpreted by the microcore control comes either out of program memory, which is fed with the program address. And if chain is 0, then I take the output of the program memory. If the chain signal is 1, I take the instruction register and feed it into the microcore control. And the instructions that need 2 cycles are from, because I have to fetch an item on the return stack in data memory. And remember, data memory access is a 2-cycle instruction. First, I have to set the address, then I can retrieve the result. Drop is the same. Exit and instruction interrupt return also needs to access the return stack memory. Query exit needs to do this. Next needs to do this if I leave the next loop. As long as I'm inside the loop, I can just access store and decrement it by 1 on a loopback and probe it whether it is 0. And if it is 0, I need a second instruction to reload, to throw away the loop counter out of store. Fetch is a 2-cycle instruction plus store I. And the if itself. Why is if and while a 2-cycle instruction? This has to do with the way the branch work. Now remember, microcore is has a postfix instruction structure. So there is a branch address in TOS, and then, no, wait a second. There is a flag in NOS that determines whether I want to take the branch or not. There is the target address in TOS, and so when I execute the branch, the conditional branch looks at NOS whether it should take the branch or not, and if it takes the branch, it takes it out of TOS. But microcore can only do 1 drop at a time in 1 instruction. So I can in this 1 instruction, this query branch instruction, I can get rid of the target address in TOS. I cannot yet get rid of the flag itself, and this therefore, if is a 2-cycle instruction because it automatically in the second cycle does a drop, and so that makes the compiler much easier, and the if behaves as we are all used to enforce. To finish my talk for today, I briefly want to give you an idea of how the bootloader works. And oops, this is not what I wanted to get. I picked a complicated example just to make the point. Microcore is on a board, and there is a serial E2PROM that holds the program for microcore. The reason is that some FPGAs allow you to pre-initialize memory areas, amongst others, of course, the program memory. But there are other FPGAs where you cannot do that. And so you need an external memory device to hold the program memory, in this case, a serial E2PROM. And so the bootloader itself has to read out the E2PROM, which is done by these 2 instructions, which is the EECFetch and the EEFetch. And the mystery is in EESet and all the interface hardware that is behind it, because reading the serial E2PROM and assembling it into bytes is done by the hardware already. So I don't have to do this in software. And so accessing the E2 memory is quite simple then on the 4th level. Then in order to be able to determine whether there is a bootable image in the E2PROM, remember, this is the cold bootloader. So when I switch on the power, the cold bootloader will be executed, and then the first thing the cold bootloader does, it executes bootcode query. And what it does, it checks the E2PROM starting at the location where the code is located, and checks whether there is a valid CRC. And if there is a valid CRC, I just assume, well, this is a valid program memory image that I want to execute. And this is the actual boot routine then, which I execute for reasons that become clear later. I first initialize the first, and here you see I use the PST instruction, which is I store a data item into the program memory. So I initialize the first two locations with 0, which are the reset locations of the reset vector. Then I check whether there is a bootable image in the first place. And if this is true, I do some address computations, and then I go into a for next loop that copies the content of the E2 into the program memory, and then I do 1+ on the program memory and 1+ on the E2 and loop go through the loop. And in the end, I just check whether the content of the first program memory locations are now different from 0, because here I initialize them from 0. Doing this instruction should have initialized them to a different value, namely a part of the address of where I want to branch for reset. And if this is the case, I put a 0 on a stack, and this no-op converts the 0 into a literal value which has no longer the lit bit set, and then the branch on a literal value is an absolute branch, and branching to 0 automatically triggers that from now on the instructions will be fetched from program memory and no longer from the synthesized bootloader. And so then I have to initialize the reset trap, and this is just initialized to boot, which I have defined here. So this is a complex bootloader that gets synthesized into microCore. And that basically finishes today's talk. But there is another slide here. Instantiations. So here are some numbers of how much space is needed by microCore. Depending on the word width, 16-bit, 27-bit, 32-bit, and depending on how extensive the instruction set is that I want. So we have the core instruction set, the extended instruction set, and the extended instruction set with floating point. And here you see the number of slices that are needed in the lattice XP2 family, and in the XP2-8 family, even the 32-bit instructions, the 32 data width version takes up about half of the size of the FPGA. So there is still some room for application-specific interfaces. And I have used up all, yeah.
When you say extended, is that just the extended?
No, this is the core plus
slices?
The extended.
Okay, consider changing the slide.
Okay, yeah, so that should read core plus extended, right? I have used up all the internal block RAMs that are available in the XP2-8, and so I left program memory always at 8K. Now remember, instructions are 8 bits wide, so these are 8K bytes. And the remaining memory I'm using as data memory. So in 16-bit, it's 6K. In 27 bits, it's 4K, and in 32 bits, I can afford 3K of data memory for a single, let's call it a single chip controller in an FPGA without any external memories. So that is it for today. And here are again 2 links. Any questions?
Yeah, can you go back to the previous screen on slices?
Yeah.
Okay, so I'm familiar with the lattice and stuff. Lattice, you know, all these FPGAs, if you synthesize a project on microsemi and then you do lattice, the number of LUTs can be quite different. For example,
Yes, they are quite different. I mean,
yeah,
microsemi is a very fine-grained architecture, and it uses up about 3 times the internal resources, and it only runs at about half the speed as all the other FPGA families of today, which have more or less the same internal structure.
So this the LFX,
there's an echo somewhere.
Yeah, that's not me. That's somebody else. So how many LUTs are, you know, this part, is this the $5 FPGA from Lattice or the $2 or what?
Oh, I don't know. This is an old one. I don't. Yeah, I think it is still being produced and cranked out. And I have a very small board which I use for experimentation. And the current cost, I have no idea. Sorry.
Yeah, because you call it slices, and some people use slices and some people use LUTs.
Okay, yeah. I think Lattice calls it slices. This is why it is slices.
Excellent. It's you did a fabulous job.
More questions?
Not a question, but I just to offer applause and thank you very much, Klaus. Anybody else? Last chance.
Ooh, I lost my. Oh no! Here, stop share. So, okay, here I'm back. Or Kevin, you are back.
I'm back somewhere. I would like to move on, if I may. A couple of notes. We survive with the kindness of speakers like Klaus. If you would like to present, I would like to strongly encourage you. I can be reached through Meetup or at forther@comcast.net. That's not .com, it's .net. Everybody here pretty much knows Klaus is raising his hand. Did you want to say something?
Yeah, I didn't want to interrupt you, but I have to add something. Okay, next time I would like to talk about the cross compiler and microCore's.
Ooh, love that.
And how it integrates with the Vhdl code.
That sounds so cool. As I was saying, if you would like to present, please contact me. We can always use speakers. If you have something, earth-shattering, globally interesting, consider presenting on 4th day, but you don't have to wait till 4th day. You can maybe give a warm-up or a preview or a globally expanded version of your 4th day talk. As you're aware, 4th day is generally consisting of shorter presentations. So please contact me. If there is somebody that you would like to hear from in this venue, you can either contact them, tell them to drop me a line, or drop me a line and rat them out, and I will endeavor to contact them. But yes, we need speakers, and yes, I don't have any other great ways of asking speakers other than to put it at the meetup message. We have several hundred folks signed up on Meetup, and as far as I know, that's the only effective way I have of contacting those people. We have you guys, and we have the SVFIG email list, and those are the ways I ask for speakers. If you've got other ways of asking for speakers, I'd be pleased to know. Bill and Don, I presume, are going to the Facebook folks and asking them to present. So it's an important thing, and I would like to encourage you to participate.